Okay, so let's go through these really quickly. We'll talk about some of the math, we'll talk about the analysis, and hopefully it'll bring up some cool conversations in air quotes, and some cool ideas. So let's get to it. So with this, what we're looking at is we're saying a proton is traveling around the Tevatron in a counterclockwise path at the instant shown below. What must be the direction of the magnetic force acting on the proton? So we're saying, okay, we are going in this counterclockwise circle, and we've talked about before, and in other physics classes, you've talked about in order to have a circular motion, what you need is a center pointing force. You need some sort of centripetal force that is bringing us towards the middle of our circle, that's pulling us back in every single time. So in this case, our centripetal force is the magnetic force. So this magnetic force is acting on the proton, and it is making it move in such a way that it will have this circular path. So our magnetic force needs to be pointing to the left in order for our proton to follow the circular path around the Tevatron. Then for this next one, we're asking what must be the direction of the magnetic field acting on the proton at the instant shown. So we know that we do have this equation that says our magnetic force is equal to Q times V times the magnetic field. And this equation, we said it's a cross product, which means that we can use our first right-hand rule for us to determine the direction of everything. So if we're looking at this, we know the direction of the magnetic force, we know the direction that the particle is moving, its velocity, which means we can figure out the direction of the magnetic field. So if I'm going to use my right-hand rule, my velocity we said is going to be upward, so that's going to be my index finger. My thumb is going to point to the left, that's going to be the direction of my magnetic force, which means if I make that shape with my hand, my middle finger has to point into the page. So my magnetic field has to be into the page. So into the page, because of that right-hand rule. And this is a proton, so we are going to be using the right-hand rule. Then if we look at this, in every single instance, we have the velocity is tangential to our circular path. And our force, we said, in order to get it a circular motion, has to point inwards towards the middle of our circle. So if we're looking at this and we kind of trace that out with our finger, with our hand, every single time you do that, if you want to keep that shape around the circle, your middle finger has to point into the page at every single one of these points. So the direction of our magnetic field is not going to be changing, which is nice. So it's always the same, always into the page. That's supposed to be an A. Always into the page. And now what we're looking at is the actual math. So we're given some numbers, we're given some data, and what we can really start out with is this idea that we just talked about. The value of our magnetic force is equal to Q times the velocity cross B. In this case, we already know the direction, so I'm just going to call it times B. So QVB is equal to our magnetic force. And then like what we said up there was this magnetic force is acting as a centripetal force. And we know our equation for centripetal force is just mv squared over r. That's an equation that we've used a bunch for the centripetal force of an object. So I can come over here and I can say, well, QVB equals mv squared over r. I have a v over here and I have a v over there, so I can cancel those out. QB equals mv over r. And I want to solve for the value of that magnetic field. So I say B equals mv over r times q. And I can plug in my values for that. Sorry, I was doing some thinking over here. So I can say my B is equal to, the mass is 1.67 times 10 to the negative 27th. My velocity is close to the speed of light, so 3 times 10 to the 8th. The radius is 1,000. And my charge is 1.6 times 10 to the negative 19th. And when I plug that all in, I get a magnetic field of 0.00313.125 Teslas. Now, this is a really interesting answer because it seems like it should be a lot quicker. It seems like it should be a much larger value. So one reason, I looked into a few reasons, but I couldn't find like a super succinct reason, but I'm pretty sure that this is where the problem lies. So hopefully we will talk a little bit about special relativity and relativity in this class. But so with relativity, one of these main equations, you guys have heard of it, is this E equals mc squared. So when objects are just moving in their normal everyday life, this is a person in their, looks like they're karate kicking. In their normal everyday life, their mass, they're not moving close to the speed of light. They're barely moving at all, not close to the speed of light. So this equation doesn't really have any effect. But if we have particles that are moving really, really quickly close to the speed of light, then this equation starts to actually mean something. It starts to actually be useful. So if they're moving closer to the speed of light, if that means that their energy is going up, right? We have a lot of this kinetic energy, which means that the mass is also actually going up because the speed of light is going to be this universal constant. So if the energy goes up because our velocity is getting so large, then the mass is actually going to increase too. We're going to have this increase in mass. So if we look at our equation again, we have this B equals mv over rq. Really, our magnetic field is probably a lot larger because the mass of these protons are actually increasing, which is odd. It seems really weird, but that's relativity for you. So that's just one explanation about why it's probably a lot larger in real life. I looked up some numbers. It's about like 1.7 for the maximum in real life, 1.7 Teslas. So we're off by a couple power 4, which is odd, but that's all right. And then the final one, there's this article that says scientists can now create a magnetic field of 14.1 Teslas inside of a particle accelerator. So I can get us to that link. It's kind of a cool link. I'll pull it up at the end. I'll leave it for now. We'll just buy into it. So why would it be useful for us to have an ability to create such large magnetic fields? So if we're looking at this equation, we say, okay, well, we have this QVB equals mv squared over r. And we can cancel out one of the v's. If our magnetic field is able to get really big, actually let me pause this really quick and think about what I want to say before I say the wrong thing. Let me pause it really quick. Okay, I think I figured out what I want to say. So when we're looking at this, we still want our particles to, we want our machine to be just as powerful. So we're not going to be changing the charge. This charge is going to be the same. We're still going to be using protons, and we still want them to be able to reach the same velocity. So really what we want is situations where V, M, and Q are still going to be the same, but now we have this increase in magnetic field. So I'm going to move this around. So BR equals MV divided by Q, where this is just constant because, again, we're not changing. We still want to accelerate protons. We still want them to be just as fast, and they still have the same charge because they're protons. So if we're able to get the magnetic field really high, that means that our radius can be a lot lower. So if we can have a larger magnetic field, we can have a smaller radius. And that's helpful because we don't want, right, if we're building this and we're thinking about cost and we're thinking about construction, it's going to be a lot cheaper to construct something like this rather than something like this. Yes, of course, we'll still have the price of the magnets and that will be more expensive. But as a thinking about the land and thinking about the environmental costs and thinking about actually building it and the construction and the materials and maintenance, it's going to be a lot cheaper to have something that a little bit smaller rather than something that's so big and taking up so much space. So that's kind of an interesting application of these physics ideas. And then here's that article that says that we can have a magnetic field of 14.1 Tesla. So this is in September 9th, 2019. And one thing that I thought was cool is they're talking about doing that by actually cooling our magnets down. So actually cooling them down and making them become more conductive. And what's interesting with that is if we're thinking about electromagnets and current running through there, it's going to be more conductive. Actually, all right, there we go. I found the part that I wanted. So it says electrical current flowing through the material generates a magnetic field. So we know that. We know that when we have current flowing, we get a magnetic field. So because the current encounters no resistance when the material is cooled to very low temperature, it loses no energy and generates no heat. So we can really crank that through there and get a larger magnetic field. So all the current contributes to the creation of the magnetic field instead of creating heat. So more magnetic bang for your electrical buck. So I just thought that was kind of interesting, and how they did that based on what we've been talking about, how the electric current can create a magnetic field. All right, so that's that with that. And then I will be giving you a free response to try out.